Hey everybody, my name is Kelvin and welcome back to my channel. Today, I built an AI profile picture detector using Python. AI generated profile pictures have gotten good enough that sometimes you can look at one and not immediately know if it's a real person or a generated image. Instead of guessing with our eyes, I wanted to build a computer vision model that tries to make that prediction for us. Here, we're going to be walking through the model that I built. It takes in a human face image and it returns two things: a label, like probably AI generated or probably real, and some confidence score like you see on the screen. Before we jump into the code and building our model, I have something I'd like to share with you. If you've been enjoying the content on this channel and want to support what I'm building here, check out my book Modern Data: From Ingestion to Production. It's a practical introduction to how data moves through modern systems, from ingestion and transformation all the way to production use. It's available on Amazon, Barnes & Nobles, and Apple Books, and the ebook is only $6, so it's a really affordable way to support the channel and learn something useful at the same time. Be sure to check out the links in the description. If you'd like to follow along, the code will be in the GitHub repository that I've linked in the description. The dataset I'm going to be using is a Kaggle dataset called 140,000 Real and Fake Faces from Kaggle. It contains real face images and generated face images, which are already organized into training, validation, and testing folders, which makes it a good dataset for a tutorial like this. This dataset will be linked in the description below. This dataset consists of 70,000 real faces from the Flickr dataset, which was collected by NVIDIA, as well as 70,000 fake faces sampled from the 1 million fake faces which were generated by StyleGAN. You can download the dataset very easily. It's around 4 gigabytes. Just go to this link, click on download dataset as zip. This will be useful if you'd like to follow along. Let's go back to our code. I went ahead and put our data into a folder called data. And within data, we have a real versus fake folder. In our folder, we have a test folder, a train folder, and a validation folder. If you open these up, you'll see that it opens up into fake and real folders. And here, this will tell us that if we click on a random image, and this right here is a fake image within the test set. And you can see that we have a very similar structure for the training set and the validation set. Now that we've looked at our data, the first thing that we should do is import the libraries that we need. We're going to be using PyTorch for the model, Torch Vision for loading images, and using a pre-trained computer vision architecture, PIL for image handling, matplotlib for visualizations, and scikit-learn for the final evaluation metrics. In our next block of code, I'm going to be setting a random seed. This helps keep the results more consistent when we rerun the notebook. Then I'll be checking for the best available device. In my case, the notebook will print that it's using MPS, which means that PyTorch is going to be using my Apple Silicon GPU acceleration on my Mac. If you don't have GPU support, it may fall back to CPU. What this is going to tell us is that the notebook is going to train using my Mac's GPU backend, and that should make this a lot faster than CPU training, although it still may take some time because the dataset is pretty large, 140,000 images. In our next code block here, we're going to point the notebook to the dataset. The dataset root is the folder that contains the train, valid, and test folders. I'm going to create separate path variables for each of those. Then, I'm going to print whether each folder exists just as a check. We want to make sure that we're actually using the correct data. Otherwise, the foundation that we're going to build our model on will be wrong. And we see that all 3 folders exists. Before the images go into the model, we need to transform them into a consistent format for our model. I'm resizing every image to 224 by 224 pixels, which is a common input size for pre-trained image models. For the training images, I'm going to also add small augmentations like horizontal flips, slight rotations, small brightness, contrast, and saturation. The purpose of the augmentation is to make the model a little less dependent on the exact images. It should learn patterns that still hold when an image is flipped slightly or has slightly different lighting. For our validation and testing sets, we're not going to be using random augmentation. I only want to resize, convert to tensor, and normalize for those. One important detail to note here is normalization. Since we're using a pre-trained EfficientNet model, we normalize the images using the ImageNet mean and standard deviation expected by that model, which keeps our input format aligned with what the model saw during pre-training. Next, we should load the images. Torch Vision has a useful dataset class called ImageFolder, and it'll automatically treat each subfolder as a class. If, say, the training folder contains a fake and a real folder, our image folder automatically will create labels for those classes. Specifically, our labels here are going to be fake and real. Let's run this code. This output tells us a few important things. First, the model will treat fake as class 0 and real as class 1. Second, we can also verify that we have all of our images, and that we have enough images to accurately test our model. This confirms two things: that the dataset is large enough for a real experiment, 100,000 training images, 20,000 validation images, and 20,000 test images, and it also tells us that we have all 140,000 images used in this project, and not some subset. Our next code block here, we're going to be creating the data loaders. The dataset object knows where the images are, but the model still needs batches of images during training, and that's what the data loader is for. For training, I shuffle the data so the model sees images in some random order. For the validation and testing, I don't need shuffling because we are only using those to evaluate. I've also set num workers to 0 because that tends to be a bit more reliable in Jupyter notebooks, especially if you're on a Mac. If you're running the script on a different machine, you can definitely experiment with increasing it. Before any training though, I want to visualize the sample images. This step is important because it gives us a very quick sanity check. If labels were wrong, paths were wrong, or the images looked very different than what we expected, we'd rather find out now than after training. Because the images are normalized for the model, I need a helper function to denormalize them before displaying them. And that's what this denormalize image tensor function will be doing. And then we're going to display a couple random images from the dataset. Looking at the samples, we can see why this task is so interesting. Some of the fake images, you can kind of tell that they're synthetic, but a lot of them will look pretty realistic at a first glance. This tells us that the model is going to need to learn subtle visual cues and not just face shape or background differences. Now that the data is loaded and visually checked, we can build the model now. For the model, I am going to be using EfficientNet-B0. Instead of training a CNN from scratch, we're going to be incorporating transfer learning. What does that mean? That means the model has already learned general image features from a large dataset. It already knows useful visual patterns like edges, shapes, textures, and lighting. Then, what we're going to do is replace only the final classification layer so the model predicts our two classes, being fake and real. For the first version, I'm going to freeze the pre-trained feature extractor and only train the final classifier layer, which makes training faster and gives us a solid baseline. EfficientNet produces 1,280 features before the classifier, and our new final layer maps those 1,280 features down to two outputs, that being our fake and real classes. The next thing that we have to do is actually define our training and evaluation functions. The first one here, train one epoch, will train the model for one pass through the training data. The second one here, evaluate model, will check performance on validation or test data without updating the weights. Inside the training function, the model makes predictions, calculates the loss, backpropagates the error, and updates the classifier weights. Inside the evaluation function, we're going to be using torch.noGrade because we are not training. This saves memory and makes evaluation faster. I'm also going to return predictions, labels, and probabilities from the evaluation function because later we'll need them for the classification report, our confusion matrix, and confidence scores. Now, we're finally ready to actually train the model. This is the code to train our model. We're going to be training for 3 epochs. 3 epochs is not necessarily the best possible setting, but it's a reasonable starting point for a tutorial. The dataset is very large, so even 3 epochs means the classifier will see a lot of images. Every epoch, I calculate the training loss and accuracy, then validation loss and accuracy. I also save the best model based on the validation accuracy. That way, if a later epoch gets worse, we can still keep the best version, and we'll let it train. Let's take a look at the results now. We see that the model improves across all 3 epochs. Training accuracy goes from about 76.6% to 77.7%. Validation accuracy goes from about 80.2% to 81.3%. One interesting thing is that the validation accuracy is higher than the training accuracy. This can happen here because the training images have augmentations applied to them, which makes the training task harder. The validation images are not randomly rotated or color shifted, so they're cleaner to classify. At this point, we see that the model isn't perfect, but it's clearly learning useful patterns. Let's visualize the training and validation curves. The accuracy curves show that validation performance improves each epoch. The loss curve also moves in the right direction, especially on the validation. Now, let's evaluate on the test set. The test set is important because it is held out from training and validation. We trained on the training set, watched performance on the validation set, and now we're going to be using the test set to get a final evaluation. I'm going to load the best saved model before testing, then we'll calculate the test loss, test accuracy, get a classification report, and a confusion matrix. And that's what this code is going to do for us right here. The final test accuracy is around 81.6%. That means the model is right roughly 8 out of 10 times on this test set. Looking at the class level metrics, the model has 85% recall for fake images and 79% recall for real images. In layman's terms, it catches more of the fake images than the real images. It also means that the model is a little bit more likely to label real images incorrectly than we might want. That really matters because in a real application, calling a real person's photo AI generated would probably not go over well. This result here is good enough for a tutorial and a first version, but it's not good enough to treat as a production-grade AI detector. To create a better model, we'll need to have access to a dataset that contains a lot more information than what we currently have. Next, we're going to convert the raw classes to friendly labels. Right now, the model returns raw class names like fake and real. For a better user experience, I want the output to say something a bit more readable. Our fake class will become probably AI generated, and real will become the label real. I intentionally use probably because, again, this model is making a prediction and not saying that this is the truth. Now, this is our single image prediction function, and that's the part where we're going to turn the model into something we can actually use. The function takes an image path, loads the image, applies the same pre-processing we used for validation and testing. Then we'll run the model, and then print a readable prediction with a confidence score. The confidence score is the model's probability for the predicted class. Again, I want to emphasize that confidence does not mean truth. It just means how strongly the model prefers one class over the other based on what it has seen. Here, I'm just going to grab a random image number. Specifically, I just chose 200 from the test set. The image is from the fake folder, so the true class is fake, and let's see what the model predicts. We can see that the true class here is fake. For this example, the model gets it right. It predicts probably AI generated with around 98% confidence. And that's a strong prediction. It means that we're assigning almost all of the probability to the fake class. But one image is not enough, so let's test one random fake image and a random real image. This is a small helper function that grabs a random image from a specific class. Then we'll test a random fake image and one random real image, and that gives us a quick qualitative check of both sides of the classifier. Both of the examples here are correct. The fake image is classified as probably AI generated with around 70% confidence. The real image is classified as probably real with around 90% confidence. And that's the output that we were working for from the start. We now have a simple label and a confidence score. I'm now going to test an image that I selected from the test folder. I've called it fakevalidation.jpg. Right now, the model will always choose either fake or real, but In a real application, forcing a label every time can be misleading. If the model is only 55 or 60% confident, it may be better to return uncertain instead of pretending the prediction is strong. The function here will add a confidence threshold. If the model's top confidence is below the threshold, it'll return uncertain. Here, I'm just going to be using 70% as an example. Let's take a look at a couple pictures. This doesn't make the model more accurate in and of itself, but it helps us make the output a bit more responsible. I'm going to use the image from before and set the threshold to 70%. Since this image had a confidence of 98.48%, it should still return probably AI generated. Let's take a look at a picture that is actually uncertain. Here, this picture is uncertain because its confidence is only 52%. It wouldn't make much sense here to say fake or real because that would be misleading. The model is so split on this, so it would not be a good idea to claim one or another. For a real application, I'd probably experiment with different thresholds and choose one based on the cost of false positives and false negatives. In this case, falsely calling a real person AI generated is probably worse than saying we're uncertain. And at the end, I have some code that'll just save our model, in case you'd like to experiment later. That means we can reload it later and run predictions without having to retrain from scratch. Now, let's talk about some steps to improve our model. The first thing I would do is not just make the model bigger. The first thing that we need to do is improve data and the evaluation setup. The dataset is useful, but modern AI-generated headshots may look different from the fake images in the dataset. A better version would include generated images from newer systems, real professional headshots, edited real photos, compressed social media profile pictures, and images with different crops and lighting. I'd also test on a completely separate external dataset to see if it generalizes. We have a couple takeaways from this project. We can train a model that learns useful patterns. In this notebook, we reached about 82% accuracy on the test set, and it was able to return clean predictions like probably AI generated or probably real with confidence scores. But we also see why confidence is not the same thing as truth. A model can be confident because an image matches patterns from its training data, and not because it truly understands where the image came from. This model here will serve as a baseline for more complex computer vision models. The next challenge here is to make it generalize. Thanks for watching, and I'll see you guys in the next video.